Good evening, everyone. I'm Daniel Austin. I'm Chief Architect at PayPal. Everybody got a PayPal account, right? Very good. All right, so this is a really fast talk, a little bit about me. In the past, I was a physicist. I worked at a place called CERN. The LHC lives there now. I ran into this guy named Tim Berners-Lee. It's all been downhill ever since. I'm going to talk today about a subject that mixes two of my favorite topics, physics and computing. So we're going to talk a little bit about quantum computing. You're not going to understand a word of this. It's okay. Next year, if I do these talks, Bianca's offered to cater us some Red Bull. It'll be useful. When people ask me about quantum computing, they ask, why do we need quantum computers? What's the difference between your analog computer, the computer you're carrying around in your wallet, your desktop? It's fundamentally, qualitatively a different animal. We use quantum logic to describe quantum computing. It's very different. The answers are not just yes and no. They could be yes, no, or maybe. And we don't always get yes or no results. We get probabilistic results. There's a 60% chance that, it's going to rain tomorrow. Well, maybe not in San Jose. But we get probabilistic results. There's also a lot of quantum mechanical effects in here. We get teleportation. We're going to talk about that in about 45 seconds. Some superdense coding, non-causal computations. That means that the cause and the effect aren't necessarily related. Multiversal parallelism, alternate universes and all that. A lot of craziness goes on in quantum computing. Quantum computing is based on circuits, which are made up of gates. These represent mathematical operators that operate on some hairy function that nobody can solve. So we use little pictures in order to illustrate these things, because if you actually tried to do those integrals, well, it wouldn't end well. The gates that we use are very similar to the ones that you studied in school. Anybody who took an EE class, took a class in electrical engineering will recognize this concept. Basically, these are gates. A signal goes through them. They're changed by the gate, and then we get a result. These are a couple examples of the sort of gates that we use in quantum computing. This is an operator. This is actually what we call a Hadamard gate. It's a good friend, that H there. We'll see it on a couple more slides. Basically, these are logic gates that we use for quantum computing. I wanted to show you what a standard quantum circuit might look like. This is actually what an algorithm might actually look like. Oh, and if you think I talk really fast, I learned that from Tim. No, seriously, anybody who's heard Tim Berners-Lee talk knows that he talks a mile a minute, and that's where I learned it. Seriously, this is what we call the Deutsch algorithm. All of this stuff here with the fanciness, what it does is it turns a 1 into a 0, or vice versa. Nothing more complicated than that. So you can imagine that if you're going to go and build, Google or Facebook, it's going to take you quite a few of these. We can't do any of that just yet, but it won't be very long. One of the craziest things people ask me about in the quantum world is quantum teleportation. I mean, this can't happen outside of the movies, right? Area 51's over here, you're over here, can't go back and forth. It doesn't really work that way in the quantum world. We can teleport information, not substances, not objects, but real information from A to B without crossing the space in between. The current record for this is about 143 kilometers. They did this in the Tenerife Island, or the Canary Islands, from the island of Tenerife to another island, and we're able to teleport some information across that gap without passing through the space in between. How that happens is a little complicated, but the schematic of the device is here. It involves a beam splitter and some mirrors. Alice and Bob are going to exchange some qubits. Qubits are the quantum equivalent of bits, basically yes, no, and maybe, not just yes and no. The diagram's a little complicated. I don't want to get into that too much. Here, once again, is the quantum circuit description of that. What's our current state in quantum computation? I mean, this all sounds like science fiction. It's great, but it's maybe the wrong convention. Maybe I should have gone to the science fiction convention. No, it's all real. It's here. Google is actually going to run one. I'm not kidding. So what's our current state of play? We can read and write 512 qubits. The D-Wave quantum computing, I think it's the D-Wave 2 model, now has a 512 qubit chip. You can buy it. Thank you. So okay. Carrying on to the next
that
part.
means time is up.
So this is the last slide on this one. We're carrying on.
Okay, well, We have to go to the next one.
That's fine.
Yep.
Well, okay, that's fine.
Yep. No.
So, that's the next slides go right in. It's fine. All right.
Okay,
so this is really just part 2.
There is a. Yeah. So if there is a segue from one to the other, I'll allow that in extra time here. So,
okay. So that kind of there was a little segue there, but.
Okay. You want to mention it now?
No, it's fine. Go ahead.
Okay. All right.
All right. So basically, the current state for quantum computation is we can do 512 qubits. We can move quantum teleportation about 143 kilometers. And we launched and put into production the first quantum computer in the world today. Lockheed did, NASA, and Google just purchased a second one, a D-Wave 2. It'll be put into production later this year. The second part of the talk is really about Grover's search, which is a good example of a quantum algorithm. In fact, it's the fastest possible search of a database. And since there's no SQL conference, I thought this might be a good topic. Grover's search is actually provably optimal for searching a random database, which is kind of remarkable. Just to give you an idea of the complexity difference here, we can run Grover in n to the 1/2 time, whereas normally we run it in O to the n or worse. Actually, most systems in the real world do worse. The gates, once again, I'm going to skip these because I showed them to you earlier and skip to the meat. This is what Grover's search algorithm looks like. This is the fastest possible search algorithm in this universe. And just to give you an idea of what's happening here, we're applying some operators to some inputs. There's some 1s and 0s over there. Those are qubits. They come in here. They go through a Hadamard transform. Then we do some work on them, and then we invert all the things that we did, and then we'd take a measurement of that. And that's what this little object here at the end is a measurement gate. We finally actually got a result. Of course, it was a probabilistic result. If you wanted to write code for this, there's multiple languages out there. I use QCL for most things. This is an example of QCL for Grover's algorithm. You can kind of see, once again, what we do here. We use the H gate, that Hadamard transform. We do an inversion. We check the phase of the bit that we're looking at. Then we undo the inversion, undo the Hadamard transform, and lo and behold, the resulting bit has the answer that we want. It's actually true. That's exactly how it works. So once again, just people ask me, so prove it. It's the fastest search, prove it. Well, one slide isn't going to contain that. This guy's going to be all over me if I try to prove it in this shorter period of time. But just to give you a flavor of the search, of the proof, any alternate algorithm will have to compute just as many iterations as Grover's does, and we can prove that, and therefore they're equivalent. The one thing about the Grover's search is it does require an oracle, which is a black box. The black box really doesn't have any function. It doesn't change the quantum nature of the algorithm, but it is a required part of this, and people ask me about that. Computer scientists talk about quantum computing as if it was some branch of computation or something. They're not physicists, right? So they're worried about complexity theory, and one of the big questions around Grover's search is, does it prove that NP, the number of normal problems, so to speak, is contained in the bounded quantum probabilistic problem set? And the answer, in my view, no. NP is not contained in BQP. Nobel Prize forthcoming next year. The number of iterations is optimal based on a constant around the square root of the number of entries. If for k entries, I'm going to have to do this many iterations over the data set to prove it. Once again, the slide is too small, as Fermat said, to contain this proof. Just summing it up, Grover's search is the fastest possible search algorithm, runs in this number of iterations for k entries. Quantum computing algorithms are based on gates and circuits defining operators that change the state of qubits. These algorithms are qualitatively different. This is not your grandfather's computing. It's fundamentally different. If you can teleport something from one machine to another, that ought to give you the idea of just how crazy it is. I mean, goodbye network, right? There's a lot of progress in this field right now. We're starting to see the first commercial implementations. New quantum language, Kipper, was released earlier this year. It's actually really useful. It's built on Haskell. I don't know if anybody's played with it. And I thought I would leave you with a small bit of advice around quantum computing. If anybody can actually read that. Okay, for my last 20 seconds, I'm speaking tomorrow, or pardon me, I'm speaking on Thursday afternoon at 1 o'clock. Even bigger topic, reconceiving the World Wide Web as a distributed NoSQL database.
Okay.
I'm going to redistribute it.
Great.
All right, well, thanks very much for having me here. That's me, Tom Stace, and I'm a physicist, so I work on quantum information and quantum computing, mostly thinking about gadgets that people might use in the future to build a quantum computer. I'm at the University of Queensland in the Australian Research Council Centre of Excellence in Engineered Quantum Systems, which has this logo. Some people think this looks like a toilet roll being unwound. And so I was asked by Arjun to give a sort of an overview of what's happening in quantum computing, and at the end I'll talk a little bit about some software open source projects that people in physics are developing, and maybe some people here will be interested in participating. I should say first that physics is at the heart of computing. So nowadays it's very easy to think of computers as sort of abstract idealizations of some information processor, but really inside everything is, of course, physical hardware that's driving it. And there was some very notable computer scientists and mathematicians and physicists over the first part of the 20th century and even back into the 19th century, which really developed the information theory behind modern computers. So I'm sure you're familiar with Alan Turing, who was a information theorist in Cambridge in the first half of last century. John von Neumann was a very influential chap who was principally a physicist, but he developed some of the very first computing systems in order to solve physics problems, often in a military context, but that's still true. A lot of the military continues to fund a lot of work in information theory. And I'll mention John Bell, Richard Feynman as well, who are both high energy physicists who had very important contributions to make to what we now call quantum information and quantum computation. And of course, one can't mention information theory now without thinking about Tim Berners-Lee, who developed the World Wide Web. I saw an interview with him where the title on the TV screen was simply listed as web developer. Of course, the web developer. And he started off at CERN as well. He was writing software for the particle accelerator. This is the state of the art. So to begin with, I'm going to sort of go through the general idea of quantum computing, and then I'll talk a little bit about quantum mechanics. So some of you may have heard of quantum mechanics. Some of you may have studied it or read popular science books about it. And I want to communicate to you today some of the strange things about quantum mechanics that are really quite counterintuitive. But to begin with, this is a supercomputer from a couple of decades ago, the Cray, and here's a supercomputer now which you can walk around with in your pocket. Maybe this is a couple of years old by now, but in fact, in many ways, this gadget is more powerful than this gadget. It has on board, it has an array of sensors with which it can measure the state of the environment, its position, its the electromagnetic environment, and it can even interact with the environment. Of course, it can make noises, and you can use it as a phone, most prosaically, and it can in fact vibrate as well, can't it? So, and here's some of the guts, shrinking what was formerly a room-sized computer into something that people carry around ubiquitously. These are some of the sensors that live inside a modern smartphone. There's electromagnetic sensors, GPS. It can sense magnetic fields. The screen, of course, is a sensor. Now, this part here has been replaced by an image recognition gadget. And there's all sorts of mechanical sensors inside it to measure accelerations and so on. And if you zoom in on some of those sensors, they occupy length scales that are really quite small, microns or fractions thereof. So here's some pictures of the accelerometers, the mechanical accelerometers that sit inside an iPhone and let it measure accelerations. And as you zoom in on them, you see these structures that are incredibly small. So here's 100 micrometers, so that's 10 to the minus 4 of a metre. So these things are at the scale of 10 microns. And if you zoom in further, you see these mechanical components, which are really test masses that move in response to forces applied to the device. So the mechanical sensors that live inside an iPhone are starting to occupy length scales that are comparable to red blood cells. Okay, so a red blood cell is a micron in size. Now, if you extrapolate the shrinking in scale from early, 2-decade-old supercomputers through to iPhones, what we might end up with in 2 decades is technologies, electronic technologies and mechanical technologies that live at the scale of, that work at the scale of red blood cells. And maybe we might have some sort of vision about what we might pack into tiny devices. And the reason that we can do that, we can envision such a future, is because there is a lot of room at the bottom. So this is a famous quote by Richard Feynman, who won a Nobel Prize in physics. He was one of the stars of physics for his generation. And he noted that when you write down the equations that govern a quantum system, the number of equations there are scales like an exponential in the number of particles. So if you have two particles interacting, there's something like 4 equations. If you have 3 particles, there's 8 equations you need to solve, and the number of equations themselves grows exponentially in the number of particles. So merely solving for the behaviour of a collection of quantum particles really requires a very large number of equations. And he realised that in some sense nature is simulating a problem that's incredibly hard to solve on a conventional classical computer. So you can get a computer like this to solve a selection of differential equations, but if you ask it to solve some number of equations which is growing exponentially, it will eventually run out of puff. Furthermore, he noticed that given the electronics of the day, and it even holds true now, there's a huge amount of space between what we do at the moment and what nature is capable of. So, for example, this is a fundamental limit to the power of a computer measured in units of heat, really. So, when the computer forgets a bit of information, there's a principle called Landau's principle, which says that a minimum amount of heat must be generated. So, this is probably a little bit warm at the moment, not yet. This is. So the reason it's hot is because it's dissipating energy. And fundamentally, when you erase a single classical bit of information, Landau's principle says that you need to generate a fixed amount of heat. It's related to the entropy generated. And the amount of heat goes like this. It's Boltzmann's constant, which is a fundamental constant, times the temperature at which it's already running, times log of 2, which is a number of order 1. And if you just work that out for a gadget like this at room temperature, it tells you that you need to dissipate about 10 to the minus 20 joules per bit that you are trying to forget, essentially. Now, if you imagine processing at the rate of a terabyte per second, then the CPU power requirements, given this fundamental limit, is something like 10 to the minus 8 watts. Okay, so that would be to process a terabyte per second. But a typical desktop computer can process, say, a gigabyte per second. That's typical bus speeds, and the CPU power consumption is of the order of tens or hundreds of watts. Okay, so there's a great margin between this number and this number. 10 to the 10 or 11 or 12 orders of magnitude, 10 or 11 or 12 orders of magnitude between what the fundamental dissipation of power that laws of physics impose on us and what, in fact, real computers do. And so, if you could exploit those orders of magnitude between the fundamental limit and what we have at the moment, maybe you can do all sorts of interesting things. But it turns out when you go to the bottom, when you ask what happens at the smaller scales, the world becomes quite strange. It becomes quantum mechanical. And quantum mechanics is characterised by the physics at very short scales, the physics at cold temperatures, and the physics at low energies. And so what I'm showing here is a micrograph of a little chip that was made in Harvard by some collaborators of mine there, where this is a surface, and beneath the surface there's a two-dimensional metal essentially. And that two-dimensional metal can be controlled by these electronic gates here. Now I won't go into the details, but essentially these gates allow you to deplete electrons from that metal that's underneath them. And you can see I've put these two little blue dots. If you tune the voltages on these metallic electrodes appropriately, you can drive this system so that there can be a single electron localized on this site here or on this site here. And that electron can be controlled, its position can be controlled. You can change the voltage on these two gates so that the electron prefers to sit on one side or prefers to sit on the other side. And you can literally count electrons out of this double well, as it's called, this two little puddles where the electronic charge can be. You can count electrons out, and I won't go into the details again, but this is an experimental result showing the number of electrons in the left-hand side and the number of electrons in the right-hand side. So 2, 2 in this region says there's literally two electrons here and 2 electrons there, and that's stable in this region. And as you change voltages, you count out electrons until you get to a point where there's none. So no electrons are stored in either of these two puddles, and if you change the voltage back up a bit, you can push an electron into the right-hand side, that's this state here, or an electron into this state here. So really people electronically can control single electrons microscopically. Now the same kind of thing happens in nature. So this is a series of length scales associated with plants. Here's 10 centimetres, you can see leaves, and then as you zoom in on a leaf, all the way down to the biochemical scale. And at this scale, photosynthesis, this is the scale at which photosynthesis occurs, light being turned into free charges with which a plant metabolises and produces things that are useful for its own survival. And quantum mechanics really does come into its own at this length scale. So up here we've got leaves which behave in the same way as everyday objects. You know, a leaf and a microphone aren't too different. If I fling one or the other, they'll crash into something. But their physics is really described by the laws of classical mechanics, Newton's laws. But down here, the physics of photosynthesis and so on, like the physics of the electronic charges on this double dot electronic device, follow the laws of quantum mechanics. So if you can push down these orders of magnitude between what conventional computers are capable of and what the laws of physics suggest that we can do, you reach a regime where you need to start thinking about quantum mechanics. So what does quantum mechanics let you do? Well, this is a sort of prelude to the rest of the talk. It's really giving you the punchline. So if you can control things at the quantum level, then what you can end up doing is building a quantum computer. And quantum computers have a few killer apps, and I'll touch on those briefly. There's not very many killer apps, but there are certainly some. And also, you can build quantum communication devices. So it turns out that with quantum mechanics, you can build essentially an encryption protocol that lets you perfectly encrypt information in a way that's provably secure according to the laws of physics. Okay, so you know that encryption that you use on the internet at the moment, in principle, can be broken if you've got a sufficiently powerful classical computer. Quantum information provides us with a mechanism which lets you generate provably secure communications channels. There's another branch of quantum technologies that people are interested in, including myself, which is thinking about what kind of sensors and measurements can you make when you take advantage of quantum mechanics. And it turns out that quantum mechanics lets you do certain kinds of measurements in a way that's fundamentally more precise than classical sensors. So there's applications in medicine and in GPS, for instance, where one can push the sensitivity of measurement devices up if you can take advantage of quantum mechanics. And in fact, one of the first applications where quantum sensors are being used is in detecting gravitational waves. So there's interferometers around, 3 interferometers around the world where people are putting quantum sources of light which have intrinsically much lower levels of noise than you could hope to get if you only knew about classical mechanics. And finally, people hope to simulate quantum systems using a quantum computer. So, for instance, if you want to design a new kind of drug for medical purposes, or if you want to design a new sort of compound, maybe a new sort of superconductor, solving those exponentially large number of equations which you're compelled to do in order to understand quantum mechanics becomes substantially easier if you can use a thing that is itself quantum mechanical to do the job for you. Now, the underlying principle of quantum computing is that information is physical. So everything that people do in quantum information is really very close to thinking about what the underlying hardware is that one's going to use. And so I just wanted to show you, so that you can keep in the back of your mind, that the things I'll be talking about in the rest of the talk really have their embodiment in different physical systems. So here's a range of different platforms that people are thinking about for building quantum information processors. So there's nuclear magnetic resonance, which you might be familiar with from medical applications. If you go and get your knee scanned, that's the same sort of device people are talking about here. There's semiconductor gadgets, the kind of quantum dots that I just showed you, the double dot where you can control the number of electrons, falls into that category. And that's essentially using technologies that are very much like the semiconductor processing that goes on to build the chips inside these computers here, but used in an application where you can control the quantum mechanical properties of the electrons. People in my university think about how to build quantum computers using particles of light called photons moving around the place. There's other sorts of electrical circuits built around superconductors where, again, one can control the state of a microscopic superconducting circuit with exquisite precision. This is called a quantum electromechanical system. It's a disk which can guide light in its perimeter, but it also vibrates quantum mechanically. So the mechanical vibrations of this thing can be treated quantum mechanically, and you have the quantum of vibrations called phonons. And finally, on this slide is trapped ions and trapped atoms. So this is a little string of beryllium atoms that are beryllium ions, which are held in a small trap, and there's literally, 7 ions held in place. And so, in fact, Griffith University in Brisbane has a lab where you can go in and you can go and see a single ion trapped in place. There's one of my colleagues is in this business, and so you can go and you can go in, and if your eyesight's good enough and the room's dark enough, you can literally see a single atom glowing. So you should keep those kind of things just in the back of your head, just that people can build a whole variety of systems which exhibit fundamentally quantum mechanical phenomenon. But what is quantum mechanics? So maybe I'll take a little straw poll here. Just put your hand up if you've heard of quantum mechanics. Now put your hand down if you, keep your hands up. Put your hand down if you know what quantum mechanics is. Okay, and put your hands down if you can't write down the Schrodinger equation. Okay, good. So people here, there's a range from, I guess, lay interest to some education about it. So that's great. So where did the quantum revolution start? Well, quantum mechanics dates back to about 100 years ago. So at the turn of the previous century, people were struck by a few fundamental paradoxes that they observed in experiments they had at the time. And so there was a period of about 50 years where people were really building up an understanding of how the physical world behaves, and some of the kinds of experiments that people worried about were the photoelectric effect, where they saw that it appeared like light came in particles, and the Planck radiation formula, where they couldn't calculate certain spectra of hot bodies from the principles that they knew about at the time. But it took some time to formulate what we consider now to be modern quantum mechanics. But once that got there, and I'll touch on some of those principles in a moment, once it got there, once we got to the understanding of quantum mechanics that we now have, it was realised that there's two really quite strange phenomena which are at their heart counterintuitive. So the first is this wave-particle duality, which you might have heard of. Now, Richard Feynman was not the person who discovered it, but he did articulate why it's so critical to quantum physics. It's a phenomenon which is impossible, absolutely impossible to explain in any classical way, and which has in its heart quantum mechanics. In reality, it contains the only mystery. Now, this was said, I guess, in the 60s, at about the time when people were starting to think about this other property in a new way, another property of quantum mechanics called entanglement. So entanglement as a concept was articulated by Erwin Schrödinger, who says it's the characteristic trait of quantum mechanics. So I'll talk a little bit about both of these principles in the next few minutes. Again, who's heard of wave-particle duality? And who's heard of entanglement? Okay. So waves, well what are waves? Waves are, you're completely familiar with. They're what happens in a pond when you toss a pebble in, and they also describe the electromagnetic environment around us. This could equally represent the radiation coming out of a radio antenna, or again, water waves. And waves have sorts of properties that you're familiar with. They can diffract through small holes. So here's a source of waves that impinges on a sheet with a small hole in it, and some of the energy in those waves propagates through that hole. But more importantly, if you have, for instance, two sources, or you puncture another hole in this barrier, you can get this phenomenon of interference. So here we've got two sources, each emitting their own waves. Each source is emitting a circular waves of this form, but where the waves add, you get constructive interference, and the waves, the amplitude of the waves builds up. And in other regions where the waves are out of phase, they cancel out, and so you get destructive interference. And if you go to the beach, you can really experience that. In these regions, you'll perceive the waves to be very powerful, and in other regions, you'll experience them as the water as being quite calm. But the other half of reality is the notion of particles. So that's what we think about when we think about something like this. It's a sort of particle-like object. It's a rigid body. It has well-defined position and momentum and so on. We can count them. And we know, for instance, where they are, and we can infer about where they might end up. Okay, this might be the Australian cricket team at the moment because it's missing the stumps. So what is light? Okay, so waves you know about, particles you're familiar with. What is light? Is it a particle? Is it a particle? Well, light does behave a bit like particles because you know it goes in straight lines, right? And you know that because, look, see this laser pointer's light's coming out here, and it's ending up quite precisely there in a straight line where I pointed it. And Newton knew that, so he proposed the corpuscular nature of light. He suggested that light was actually made of particles. But over the ensuing centuries, people became increasingly convinced that light, in fact, is wave-like, and Thomas Young demonstrated the double slit, or so-called Young's interference experiment, which is exactly the one I showed you before. You have a source of waves, source of light, that can propagate through one of two slits, and what you see here is an interference pattern where there's regions of high intensity light and regions of low intensity light. So this is just the conventional interference effect you know about from water waves. There's some where the phases of the waves add up, you get large amplitude and large powers, and where the phase of the light interferes, you get regions of dark. And so it was known before quantum mechanics that there's the potential to think of light in two different ways. And the question is there a sort of Rosetta Stone? Is there a way to decode the nature of light? What is it? So here's a little representation of the Young's double slit experiment where you have a source of light that illuminates two pinholes, and then there's a screen here where we observe what happens. And again, I guess I've gone through this somewhat. So if light is wave-like, well, you expect it to exhibit interference. And if it's particle-like, you expect just the arrival of the particles to, particles don't interfere, that is, where one particle ends up and where another particle ends up are sort of independent of one another. So you expect, if light is like a particle, then you shouldn't expect to see interference. And in fact, what you do see, as Thomas Young observed, was interference. So light certainly does behave like a wave. But sometime later, when people could start detecting light in its, could start measuring the smallest energies available for instance, in photographic film, when light arrives at a photographic film, it can be shown that it arrives in little individual packets. That is, if you have a very low intensity source of light, maybe a candle, very distant candle, and you expose some film, you see not a general lightness of the exposed film. What you see is certain pinpoints where the light appears to have arrived in small packets of energy. The light doesn't just arrive in a diffuse way; it arrives in this packet-like way. And so if you build a single slit experiment, that is, you have a source of light that's very low intensity, then the light from that builds up in these small packets, and of course there's a single trajectory from this source to the screen, and so you get a bright pinpoint of light at the screen. You can see here there's the other slit's covered up. So what happens if you uncover the other slit? Well, now there's two possibilities. The particles of light, which we know about because that's what arrives at photographic film when you develop it, you see these pinpricks of light. The light could come through this slit or it could come through this slit. So you'd probably expect, if you believed light to be particle-like then, to see just a bright streak here and a bright streak at this point. But what you see is this interference pattern. So how does that build up? Well, as single photons from this source pass through this region here, they build up over time, and they tend to arrive more frequently at these bright areas and less frequently at these dark areas. So light is simultaneously behaving like a particle because it only arrives in these small pinpricks. It doesn't arrive diffusely over the entire film, but over many iterations of this, where you have very many photons arriving, you see them collect in regions of these bright streaks and not collecting in these regions of these dark streaks. So there's something very strange happening. Light's coming in minimal packets of energy, indivisible packets of energy, and it's arriving nevertheless as if it were a wave. So what is light? So here's an experiment which really gets to the heart of the nature of light. So here's a beam slitter or a half-silvered mirror. It's the sort of thing that you might see in cop shows, you know, where they're trying to spy on somebody who's giving evidence, and so it lets some light go through, and it has some reflection as well. So light can be reflected or it can pass straight through. And if you build some very sensitive detectors, which are quite commonly available now, and you shine a particle of light into here, the light will, the photon, the particle of light, will arrive at one of those detectors or the other detector, and in the language of physics we say those detectors go click, because that's the nature of a Geiger counter, for instance. You know, you hear these sequence of clicks. And the probability of one or other of these clicking is 50% for each photon. The photon has a 50% chance of arriving here or arriving there, but that's just like a marble that you fling at some stick that it can bounce one way or another way. So there light is behaving just like you would expect for a particle that's randomly being distributed one way or another. Light acts like a particle. So here's another experiment. It's same gadget here, and then there's a fully silvered mirror here, so this bounces the light up there, and then there's another half silvered mirror here. And on this branch, we're just going to put an absorbing block, some black stuff here. And what happens? Well, if you put a photon in here, there's some chance it'll be reflected and crash into here. There's some chance it'll be reflected into this detector and click there. And there's some chance that it will end up in the other detector. Okay, so these are the possibilities. And if you do this experiment many times, you find about a quarter of the photons that end up here, a quarter end up here, and half of them end up here. Okay, so that's just what you expect if you're flipping coins at each of these at each of these. So at this point, we're going to flip a coin and just decide, did the photon go that way or that way? At this point, we're going to flip another coin and say, did it go that way or that way? So light does behave like a particle. Well, here's just a slight modification of the same experiment. We're going to remove the block that was here. We've got a half silvered mirror there, half silvered mirror here. Now, let's just do another straw poll. Let's say, put your hand up if you think that that this photon, if we put a single photon in here, it'll end up at either of these detectors. There's some possibility that it'll end up here or here. Put your hand up if you think that's what'll happen. Okay, that's a pretty good guess. What if you think it will end up definitely here? Or definitely here? Anyone? Well, if you do the experiment and you tune things correctly, in fact, you can design it so that it always ends up at one of these detectors. No matter how many times you do it, the light always comes out this port here. Okay. So this you can do in the lab. You can send a single photon in here. It's got 50% chance of going one way or the other here. You'd say it's got 50% chance of going one way or the other here. So on average, you'd expect half of them to end up there and half here. In fact, in the experiment, they can always end up here. Okay. So even though these are both flipping coins, in some sense they're correlated, right? So the coin flipping conspires to send the photon always out one port. So that's kind of strange. How can a particle do that? Well, the answer is that particles can't, but waves can. So this is the wave interpretation. So we put a wave into this thing, and the wave's got some part of the wave is transmitted and some part is reflected. And then the wave, those two parts of the wave propagate along, and they arrive at this beam splitter. And then at the two outputs of these beam splitters, on one port, the waves add up constructively, and on the other port, they add up destructively. So the total power in the wave coming through here, if we just think about water waves, is 0, and the total power coming out here is all of it. So all of the light, when you think about it as a wave, goes in here and comes out here. So that's perfectly reasonable if you're happy to think of light as if it's a wave.
Question.
Mm-hmm.
Does the wave go faster than the particle, than the photon?
The wave and the photon are not different things. Okay.
That would be strange.
That's, yeah, well let's keep going and we can have a chat. So we've seen this picture, you can send it one way or another. And so now we might want to, so sorry, I've just got myself lost. Yeah, okay, so, sorry, my slides have done something. So I guess what I'm going to show here, you can do an experiment now where you play a trick on light. So the light, let's say we set up an experiment, and people have done this. You set up an experiment in which this block is possibly there or possibly not there, and you make these arms long enough so that light takes a long time to propagate through. And we're going to make a choice about whether that block lives there only after this photon has passed this beam splitter. So here's the picture. We're going to set it up so that the photon definitely goes, well, it goes one way or the other way. It's gone through this beam splitter. And at that point, we can make a choice. And the choice is we can put a block there after the photon's gone through here. And if we do, then the light ends up at these with 25% probability, as I said before. Or if we remove the block after the photon's gone through, then we recover this picture where the light goes through. So it's not the experiment is a funny one because we're making a choice about whether this block is here only after the photon has gone through there. So in a sense, the photon has to decide before the block appears whether it's going to behave like a particle or a wave. So it's not a particle and it's not a wave. At this point, it's indifferent, right? It doesn't know. And it can behave like a particle or a wave depending on the nature of the experiment that you do. And people have done this, in fact, not just with light, but with all manner of particles. So electrons behave like waves, as do atoms. And in fact, the largest molecule people have done this kind of experiment with is a buckyball, which has 60 carbon atoms in it. So people have built interferometers, this is called an interferometer, in which you see quantum behaviour of all these particles that we conventionally think of as massive particles. Now, electrons you're in fact not unfamiliar with. That's electron microscopy. And any time you see an image of an electronic gadget where the feature size is less than the optical wavelength, so if you see a picture of a bit of electronic hardware where you're looking at things that are tens of nanometers across, which is the size of the electronic elements inside this CPU, anytime you see an image of that, it's actually because electrons are diffracting around those metallic features as if they're waves. So the electrons in an electron microscope are really behaving like waves. What time do I have to go till, by the way? 5:15, is it? Okay. So this picture that I've shown you, where you put a photon into a half-silvered mirror and it can go one way or another, if you think about it for a moment, affords a way to encode information. So if I want to encode a bit, I can write 0 or 1, but that's changing the physical state of a piece of paper. I've either written 0 or I've either written 1. And likewise, the state of a photon, whether it goes on one path or another, can be used to encode information. So you might imagine I'm going to describe the state 0 by the physical situation in which light goes through along one channel, or 1 is when the light goes along another channel. You can also do the same thing for polarization. So I could say a horizontally polarized photon, that is light that goes through sunglasses that are held in one orientation, is going to denote the 0 state. Light that goes through sunglasses that are twisted by 90 degrees is the vertical polarization. We might denote that as the 1 state. So the physical state of the light, which path it goes through, which polarization it has, can be used to encode information. And there's a variety of other properties of light that can be used also to encode information. When the photon arrives, can encode information. The shape of the photon can encode information. So whenever you think about information in this quantum picture, you should really think about the possibility to represent that information in a variety of different physical systems. So I showed you this already, that one can build an electronic device where an electron can be localized on one side or the other of this little island. And that, likewise, can represent a bit, right? So if the electron were on this side, we could call that a 0. If it's on this side, we can call it a 1. And similarly, this is a cloud of atoms that a friend of mine built in his lab. It's a cloud of beryllium atoms, and the internal state of each of these atoms can take one of a variety of configurations, and you can encode information in there. And here's some other devices. This is a superconducting gadget, as is this. This is the mechanical oscillator that I was talking about before. Each of these things has been proposed as a mechanism by which one can store information in this intrinsically quantum way. Just as I said, photons can be in a state 0 or 1. Those things likewise can be in states that are 0 or 1. Now there's this other notion in physics called entanglement, which Erwin Schrödinger first originated in 1935, and what he was trying to get at with that idea is that in quantum mechanics you can write down states of systems that are inexplicable according to the laws of classical probability, and it's very strange. It needs an analogy. And I noticed on the brief for my talk, it was promised that I might make a joke about Schrödinger's cat. So here's a cat and here's an atom, but you know the Schrödinger cat story. Paradox is that we have a cat in a box and there's an atom here somewhere that decays. If it decays in some interval of time, it triggers a hammer to break open a vial of gas that kills the cat, and if it doesn't decay, then the cat lives. So after some interval of time, is the cat alive or is it dead? And what we say quantum mechanically is that we write the state of the system like this. So if there's no decay, sorry, this is back to front. If there's no decay, then the cat should be alive. Let's invert the thing. If it doesn't decay, then we've got some other trigger that causes the cat to die. This is the inverse Schrödinger's cat. and conversely, if there is a decay, then it stays alive. So I'm sorry, I got those back to front. This is what we write down quantum mechanically. Now, this is a mathematical expression, but physically what it's saying is that there's some possibility for this to have happened as well as some other possibility for this to have happened, just like light taking one path or taking the other path. There's an infinity of jokes about Schrodinger's cat. You can read some of those. It was promised that you'd get some Schrodinger's cat jokes, wasn't it? So I won't bother repeating them. You can read them there. Now, entanglement's a strange thing. So Einstein, this is Einstein with Herbert Hoover, the US president. Einstein was obviously a very bright guy, and he believed that this funny correlation, that you could have a superposition, you could have a state in which something was both alive and dead, correlated with the state of this atom that had decayed or not decayed. He believed that indicated that quantum mechanics was incomplete. And what he said was that that there's some intrinsic, the fact that there's some intrinsic probability left over in the theory of quantum mechanics, that is, you can have a state in which the final outcome is not determined, tells you that, in his opinion, that it doesn't provide a complete description of the universe. So in Einstein's opinion, and it's a very reasonable opinion, a complete description of the universe should allow you to predict with certainty the outcome in the future. And he correctly recognised that quantum mechanics doesn't let you do that, which he felt was a flaw in the theory. That there should be some underlying theory that was more complete than quantum mechanics, which would let you discriminate between the two possibilities in the future of the cat being alive or dead. Then a little later in the mid-60s, John Bell came along. He was a high-energy physicist in CERN, and he realised that Einstein had identified a really Einstein's insight was key. So what Einstein believed was that quantum mechanics was some sort of effective theory, and that underlying it there was some, what he called a hidden variable. There was some variable that those particles would have, the cat and the atom would have inside them, that would tell future experiments what reading to have. So for instance, when I showed you the interferometer, the photon goes with 50% chance one way and then another way, and then it recombines on another beam splitter with 50% going one way, 50% going the other way, but things conspire for it to come out the other, only one port. And what Einstein thought in these terms was that there was something about the photon, something inside the photon that kept track of which port it should come out in the future, and he called that a hidden variable theory. And he wanted to do that because in that case there would be some property about the photon which maybe we don't have access to because we're not clever enough, that would somehow determine its future. And what Bell realised was that there's an experimental test one could make that would distinguish that proposition that particles have this hidden variable which determines their future, just like you expect if I fling this microphone over there, it's got a bunch of properties which determine where it will land. He proposed that in fact there's an experiment that can distinguish between that notion of a hidden variable theory which determines with certainty the future outcome of experiments, with what quantum mechanics predicts, which is that in some circumstances you simply can't predict if the photon's going to come out one port or the other. And he cooked up a very simple experiment, which I won't go into at the moment, which would let you distinguish whether a hidden variable theory was a possibility. And if the experiment turned out that way, then fine. We could continue to believe that things do behave according to some internal property. Or if they work out a different way, that is, if they work out in the way that Einstein was incredibly uncomfortable with, it would imply that quantum mechanics is in fact not just correct, but actually also complete. That is, it provides a complete description. And in that case, it would suggest that either the hidden variables exist and something happens faster than light could be responsible for. Some information is propagating at a rate faster than light. Or conversely, there's correlations that exist that are inexplicable under the conventional laws of classical probability. And there was an experiment that did that in 1982 that established that by Alain Aspect, which established that in fact it is that this is the correct proposition. So either there's some signal that travels faster than light, or quantum mechanics can't be explained with conventional probabilities. That is, he showed that what Einstein believed to be a fundamental problem with quantum mechanics was in fact its key strange property, and it was really the case that the laws of physics do not allow you to determine with precision what's going to happen in the future. Now, I showed you these pictures of the nature of a single photon that could either be in horizontally polarised, in which case we call it a state 0, or vertically polarised, in which case we call it a 1. And with light, for instance, it's very straightforward to understand what we mean when we try and add these two things together. When we add something that's, when we have a wave which is horizontally polarised and we superpose it with a wave that's vertically polarised, what we end up with is a wave that's diagonally polarised. That is, you add these two things together like vectors, if you know what a vector is. And a similar thing happens if you encode information in the position of the photon, whether it went along here or here. Although in this case it becomes quite a tricky thing to imagine. What is it to add this thing to this thing if they're one photon? That is, what is the state where the photon has some probability to be here and a probability to be here simultaneously? In this case, it's very obvious. It just means that the polarisation of the light is diagonal. But in either case, in quantum mechanics, we write it, as I've shown already, in this mathematical form, which is just like adding vectors. So if you think about adding vectors, that's what you get here. A vector that's horizontal plus a vector that's vertical will give you a vector that's diagonal. So that's what gets written down. That gets called a wave function in quantum mechanical language. But what if we had two photons and we put those two photons into a funny sort of interferometer, a funny sort of beam splitter, where both photons would go one way or both photons would go the other way? Or perhaps if we're thinking about polarisation, both photons have horizontal polarisation plus the possibility that they both have vertical polarisation. And this is a state which is entangled because now those two photons they're correlated. So if we look at one photon, then we know for sure that the other, if we look at one and we find it's horizontally polarised, we know for sure that the other one was vertically polarised. Conversely, if we look at them and we find one is vertically polarised, then for sure the other one's vertically polarised as well. But the two photons together are simultaneously in both possible states at once. And so this is really the clue as to why quantum information is special. So classically, it makes no sense to write this. If I tell you that a bit in that computer is in some hybrid state of 0 and 1, then you would say that there's been an error. Okay, it doesn't make sense classically to talk about information being simultaneously in the state 0 and 1. And it becomes even stranger to say that two registers in a computer can both be in the state 0 simultaneously with both being in the state 1. But that's really what happens. So let's think about what the state of a computer might look like. So classically, again, you can identify bits as being in the state 0 or 1, and maybe we can picture that as being an arrow pointing up or an arrow pointing down, just pictorially. And for instance, a 3-bit register can store one number, which can be any number from 0 to 7. So we can store one n-bit number in an n-bit register. If instead of classical bits you have quantum bits, now we can still think of the computational states as being 0s and 1s, which have these sort of orientations in this pictorial way, and we can add them together. We can add states together, just like I described. So this would describe diagonal polarised light if this is horizontal and vertical, and this would describe circularly polarised light, things which you actually have some classical experience of if you've ever used polarised sunglasses. But when you think about several photons or several quantum bits together, you can end up writing these kinds of states down. A single quantum register can simultaneously be in all possible configurations of 3 bits at once. Okay, now that's very strange. Okay, but nevertheless it's true. A quantum computer can represent all possible 2 to the n numbers. An n-bit quantum computer can simultaneously represent all possible states of a computation simultaneously. Now classically this is the kind of gate that you think about at an elementary level. This is a NAND gate, and here's the truth table. And in this case this is irreversible. So if I just tell you the output, you can't uniquely tell me what the input was. In fact, classically you can build reversible computers. So you can build a gate whose output is uniquely determined by its input and vice versa. So given each output I can map it onto a unique input. And so you can in fact build reversible computers, classical computers. Quantum mechanics has an equivalent sort of gate, but in quantum mechanics, there's a certain rule which I won't go into, the quantum computer must be reversible. So every gate in a quantum computer has to behave in some sense like this. That is, the output each output is uniquely determined by the input and vice versa. But in this case, there's another requirement, which is that the gates must be coherent. So that is, if I put in two inputs, say in the state 0 and 0, then the output for this controlled NOT gate is this one here. And you can see the truth table. The only important thing is that it does a NOT on the second bit if the first bit is in the state 1. So it flips the second bit contingent on the value of the first bit. Now here, every output is uniquely determined by the input and also vice versa. But one needs to build this gate in a way that's coherent. That is, if you put in a state here that's in a qubit into one port that's state 0 and the other in this funny admixture of 0 and 1, then the output has to be this, what we call entangled state. So it's a special kind of gate that has to satisfy this kind of this property. Now the strange thing is, as I implied earlier, is that in a quantum computer, a 300 qubit state, if we tried to represent that in a classical computer, would require 2 to the 300 complex numbers. Now that's more numbers than there are particles in the universe, and so a 300 qubit computer is not very large in principle. It could be something that fits inside this this bench. If we were to try and represent the state of that with a classical computer, we'd need every single particle in the known universe. And that fact means that there are certain problems that I won't go into the reasons for, but we can, in principle, solve exploiting this quantum language of superposition and entanglement to solve in a way that's more efficient than a classical computer. And now these are the killer apps that I was referring to earlier. The first is factoring. So you know that factoring is at the heart of encryption protocols that we use at the moment. And it turns so if you use a classical computer to try and factor a number, this is the computational complexity, and it turns out that it's a hard problem. Okay, the best factoring algorithm that we know of publicly is exponentially hard. But if you had a quantum computer, the complexity of that problem becomes polynomial. So in principle then, if we had a quantum computer, you can factor arbitrarily big numbers in a time that's not unreasonably long. So you could break all the internet encryption that you're probably using right now. It turns out that there's a certain way to phrase search problems in which you also get a speed up, not an exponential speed up, but you certainly get a speed up beyond the best known, provably best classical algorithms. It turns out there's a variety of other problems that exist in simulating compounds, chemical compounds, which if we had a quantum computer we could do in a time that's polynomial in the size of the problem we want to solve. That is to say, it becomes tractable. So there are advantages that computational advantages that one can achieve if you can exploit this these weird quantum effects of superposition and entanglement. There's a trade-off though, because quantum computers are incredibly sensitive to errors. Okay, so this is from a paper that Google published, where they looked at the DRAM error rates in their clusters, and they found that they were getting something like 25 to 70,000 errors per billion device hours per megabit. And if you work that out, it's something like 10 to the minus 13 errors per bit per second. Okay, so that's pretty slow, the error rate, right? So that's telling you that classical memories are incredibly well engineered. They fail only 1 in 10 to the 13 seconds. Each bit fails with the mean time between failure of 10 to the 13 seconds. And about 8% of DIMMs were affected by at least one error in a year. But that's pretty amazing because DIMMs have got many millions or billions of bits inside them. But quantum computers need to be protected from errors because whilst errors in a classical computer take the form of either a bit flipping from, let's suppose we wanted it to be 1 and flip to 0, or perhaps it simply can't take one of the states that you wished it to. So there might be some reason that it's broken and it's always stuck on, say, the state 0. There's another possibility in quantum mechanics, which is that if some gremlin in the machine somehow manages to infer the state of this particle, and in the language of quantum mechanics we'd say they're measuring that particle, suddenly you collapse this superposition, as we call it, into a probabilistic mixture. So now the system is no longer in a superposition, but it's in just a conventional probabilistic mixture with 50% chance being in the state 0, 50% chance being in the state 1. That's just like flipping a coin. And with coin flipping you can't do very much. I'm really getting close to the end now. So I'll just allude to the fact that there are very powerful techniques that are being developed now in quantum error correction. So they borrow from the field of classical error correction, which was developed for classical computing, but in fact, by and large, is not really necessary inside that computer. But classical error correction is a well-recognised field, and there are quantum error correction protocols that people have developed. Now I'm well over my time, but so that's really an overview of quantum information and quantum computing as it stands at the moment. People really are building quantum computers. You can in labs there are quantum computers with of the order of 10 quantum bits, and people can do calculations with those. They're still very primitive compared to say a classical computer with many billions of bits, but nevertheless they do exist in the lab. Getting to the point where they become useful to solving, say, factoring or some of these simulation problems will require another factor of 10 or 100 quantum bits to be built with all the quantum error correcting infrastructure around that. But suffice to say, people are well on the way to building quantum computers. And I wanted to finish, because this is an open source conference, I wanted to finish with a few projects in quantum information where people are really trying to develop software to control their quantum computers. So behind the scenes, whenever you build a quantum computer, there's error correction, or there might be some other processing that needs to go on in a classical computer. And people have been working hard at the kinds of problems that one would need to solve in order to run the underlying classical hardware that keeps the computer going. So I'm going to show you three different projects that people are working on. So there's a kind of classical simulation technique called matrix product states. I won't go into the details. It's a graphical and mathematical way to represent quantum states. And there's a guy at UQ, Ian McCulloch, who's writing this software, Matrix Product Toolkit. And so if you look that up online, you'll find this software that he's developing. And it's a very powerful technique for simulating quantum systems, some restricted class of quantum systems on a classical computer. Similarly, there's another project, XMDS, which is really a software package for solving differential equations, certainly ones that are pertinent to quantum mechanics. There's a Schrödinger equation, which is the governing equation of quantum mechanics, and this is just an example that's on there. So this is being developed by a chap called Joe Hope, who's at ANU, and it's some way along the way to being quite usable. And then finally, before I finish, there's a package called LabScript, which is being developed at Monash University, which is really trying to open source the control of a laboratory. So given some experiment that people might wish to do, the hardware that you need to control to make sure that all the atoms are where they need to be and where the photons are where they need to be and so on, it can be incredibly complicated. If you look at one of the experiments that they build, they're very large optical tables with hundreds or thousands of gadgets. And so there's a real problem with ensuring that you can build an experiment that's repeatable and reliable. And so these are just three open source problems that people are working on. And I'd encourage you to go and have a look at those if you're interested in participating, because I wanted to end just to say that physicists are good at doing physics, but not necessarily great at doing software development. So of course, we can get things going, but they're often sticky tape and blue tack affairs. So once the thing's built, it works until you take the data and then you write the paper and then you go on to the next thing. But to go to the next step where you have a sophisticated underlying engineering solution that is reliable and will let people build on that work in the future is something that we don't have the time or the skills necessarily to pursue. And so I'd encourage you to go and have a look at these. And if you're interested in getting involved in developing software for the physics community, working with physicists to write software, then get in touch with me, and I can at least start the conversation. So I'm well over time. Thanks for having me, and hope you've enjoyed your workshop.